Today we'll continue our topic Cauchy Riemann equations as we have been discussing in our last video. And let me recall what were the Cauchy Riemann equations in Cartesian form, and those were, I should write the criteria of analyticity, right? Fz is analytic on domain D if and only if the first condition was the Cauchy Riemann equations, and those were ux is equal to vy and uy is equal to minus of vx, right? And the second was uv, ux, uy, vx and vy are continuous, right? So taking some more examples, I will take another example. Example number 1, discuss the analyticity of fz equal to 2x square plus y plus eta times y square minus x, right? So this is a function given in terms of x and y, right? And we have to discuss its analytic behavior, right? And we have to rely again on these Cauchy Riemann equations and plus the continuity criteria of these functions and their partial derivatives, right? Solution. So first, picking up the value of u and v. This is a real part of complex function and this is the imaginary part of complex function. So here u, more precisely we can write it as u of x comma y, because u will be a function of x and y, equal to 2x square plus y and v equal to y square minus x, right? And finding their partial derivatives, that is, then del u over del x is equal to 4x, del u over del y equal to 1, del v over del x equal to minus 1 and del v over del y equal to 2y, right? Fine. And you can see that u, 2x square plus y, v, that is y square minus x, they both are continuous function on the whole complex plane, right? As they are not in fractional form, right? And their partial derivatives 4x 2y minus 1 also they are continuous on the whole domain D, right? Means the condition number 2 is satisfied. The continuity condition of u and v and their partial derivatives is satisfied. You can see that. But what about this condition number 1? Means ux should be equal to vy. If you see that ux is not actually equal to vy, but uy is equal to negative of vx. You can see that uy is equal to negative of vx. So this condition is satisfied, but this is not satisfied, right? Now ux equal to vy gives, if you put ux equal to vy, that will give you 4x equal to twice of y, and that will give you y is equal to 2x, right? And we already have uy equal to minus of vx, right? So Cauchy Riemann equations are satisfied if y is equal to 2x, right? And y is equal to 2x is an oblique line through the origin. It means that the Cauchy Riemann equations and the continuity criteria of u, v and its partial derivatives are satisfied on this line y is equal to 2x, right? So what can we comment about the analytic behavior of fz? Should we say that it is analytic, or should we say that it is differentiable, right? You have to think it geometrically rather. Imagine this line y is equal to 2x, right? I will draw this line. This is x-axis, this is y-axis, and y is equal to 2x is a line through the origin, right? This is line y is equal to 2x. And you can see that the Cauchy Riemann equations are satisfied along this line only, and there are so many points, infinite number of points on this line. But since the analyticity is a neighborhood property, not a point property, so we cannot declare that this function is analytic, because if you imagine that this is line y is equal to 2x, and if you take any point of it, and we know that since CR equations are satisfied over this line, taking its arbitrary point on this line and drawing a small neighborhood of it, and that will be a small disk, right? And there will be infinite number of points on that disk, means the upper part of the line and the lower part of the line. There will be so many points. I will draw that disk here like this one, right? And you can see that there are so many points, these points, and the points below the line where the function is not differentiable, right? And you need some neighborhood so that the CR equations are satisfied on it, right? But on this line, the CR equations are satisfied on this point only, at this point only, not in the neighborhood of it, right? That means this function is differentiable at along this line, but not analytic, right? So this y is equal to 2x, and this is the neighborhood, a small neighborhood, right, at some point, and that point is x naught comma y naught, and let me take that y naught is equal to twice of x naught, right, on which CR equations do not hold, right? And hence we can say that therefore fz is differentiable, right, at all points lying on y equal to 2x, right? And it is nowhere analytic, right? Because analyticity is a neighborhood property, and you cannot draw any neighborhood of any point lying on this line such that the function is satisfying the CR equations there, right? So this is one of the example, taking CR equations, right? And let me take another example, and example number 2 show that fz equal to x cube y to the power 5 x plus iota y divided by x to the power 6 plus y to the power n when z is not equal to 0 and 0 z is equal to 0 satisfy CR equations at z equal to 0 but not differentiable there, right? So this is another type of example in which the function satisfies the CR equations at that point, but the function is not differentiable at that point, right? And let me check this CR equations first, but one thing you should notice that you have to check the CR equations at the point z equal to 0, right? Means those del u by del x and these are all four partial derivatives are required at some particular point, and in this case we can use another formula to find the partial derivative at a single point, and those formula as we derived these CR equations, this CR derivation of these CR equations, use those formula, right? And I will rewrite those formula. You can refer them in the derivation of these CR equations, right? And those formula were solution. I'm writing the formula for all these partial derivatives at some particular point, and that is del u by del x, and obviously we are finding the derivative at 0 comma 0 is equal to limit h tends to 0 u 0 plus h comma 0 minus u 0 0 over h, right? In general, here we have del u by del x small a comma b, right? And in that case u a plus h comma b minus u a b over h, right? And this is a partial derivative with respect to x. So increment of h should be given to x only, right? Okay. So u 0 comma h comma 0, uh comma 0, and first we have to find the u and v from here. I will first write the formula. Okay, right here I will write where u x comma y equal to, the value of u should be the real part of this function, that will be x to the power 4 and y to the power 5 over x to the power 6 plus y to the power 10, and v x y equal to x cube y to the power 6 over x to the power 6 plus y to the power 10. Right, fine. And you can see that if you find comma 0, comma 0, substitute x equal to h and y equal to 0 here, you will be getting h to the power 4 multiplied by 0 divided by h to the power 6 plus 0, and that will be ultimately 0, right? Limit h tends to 0, 0 minus u00, right? And it means that u00 means x equal to 0 and y equal to 0, and that means that z is equal to 0 because x plus eta y is equal to z, right? And for z is equal to 0, the function is explicitly defined at z equal to 0, and the value of the function is 0, right? So I have to write 0 here, fine, using this one, not this one, okay, upon h, and that will go to 0, right? Similarly, the partial derivative of u with respect to y at the point 0, 0, the formula will be almost similar with only one change, and this time we have k tends to 0, and since we are finding the partial derivative of u, and but with respect to y, so there will be an increment of k for this yth ordinate, right, y ordinate, minus u 0, 0 divided by k, right? And similarly you can find u0 comma k from here, right? If you put 0 comma k, then it will be 0 multiplied by k to the power 5, and that will be ultimately 0. So limit k tends to 0, 0 minus again u00 will be given by this one, by k equal to 0, right? And then del v over del x at 0 comma 0, limit h tends to 0. This time we are finding the partial derivative of v with respect to x, and the formula will be v 0 plus h 0 minus v 0 0 over h, right, equal to limit h tends to 0. This time I have to use my v, and this is my v. You input in place of x put h, and in place of y put 0. You will be getting 0 here, right? 0 minus 0 over h, and that will be 0. And similarly the last derivative del v over del y at 0 comma 0 will be limit k tends to 0 and v 0 comma 0 plus k minus v 0 0 over k, and ultimately that will be 0, right? And these are the Cauchy Riemann equations at point z equal to 0, right? Okay, so you have to remember these formula, and you can see that del u over del x is actually equal to del v over del y. You can see that del u over del x is equal to del v over del y, 0 equal to 0, and del u over del y is equal to negative of del v over del x, 0 equal to 0. So we can say that Cauchy Riemann equations are satisfied at the point z equal to 0. You can see that all of them are equal, 0 0 0 0, right? Clearly CR equations are satisfied at z equal to 0, right? Means the first condition is satisfied, CR equations, right? Okay, but you have to show that, see here, given that you have to show that the function is not differentiable at z is equal to 0, right? And obviously if the function is differentiable at z is equal to 0, then f dash 0 should exist uniquely, right? And we will use the formula of derivative as we have used in our last videos, the differentiability of complex valued function. So I will be using that formula, right? Using the formula of derivative f dash 0, right? And the formula is fz minus f0 over z minus 0, and limit z tends to 0, right? And the general formula is, I will write the general formula. In general, f dash a equal to limit z tends to a fz minus fa upon z minus a, right? And the formula is very similar to the formula of derivative we use in case of real function. That is, the derivative at any point is a ratio of the change in the values of function divided by the change in the values of the input, right? Means fx minus fy upon x minus y, right? And you can see that the formula is quite similar to that one, right? Okay. Then fz minus f0 upon z minus 0, then I will use this value of fz, this value, and then f0 is 0 and then z minus 0, and we'll see that whether this limit exists or not, right? Okay. Right. Then implies f dash 0 equal to limit x comma y tend to 0 comma 0, right? And fz is this value, x cube y to the power 5 x plus iota y over x to the power 6 plus y to the power 10, and then minus f0, and that is obviously 0, so it will be minus 0, and divided by z minus 0, and the value of z is x plus iota y, so 1 over x plus iota y, right? And you can see that everything is converted in terms of x and y, right? So I have written xy tend to 0, 0, fine. And this x plus I factor will be cancelled out, and you will be left with uxy implies 10 to 0, 0, x cube y to the power 5 x to the power 6 y to the power 10, right? And now comes the selection of the curve, right? Curve through the origin. As we have discussed in our last videos of differentiability, we choose different curves passing through the point 0, 0, and we see that whether the limit is unique or not, right? So I will choose let me choose suppose choosing or approaching z equal to 0 along the curve y to the power 5 equal to m x to the power 3, right? Okay. And you can see that this curve passes through the origin. If you put x equal to 0 and y equal to 0, then it shows that this passes through the origin, right? We have to choose some curve which passes through the origin, and it is not the case that every time you will put y is equal to mx, right? The selection of the curve is important, because if you will put y is equal to mx, then here in the numerator I will have x to the power 8, and in the denominator I will have x to the power 6 common. Now in that case x to the power 6 will be cancelled out, and you can get the wrong result, means you can get a unique limit, right? Okay, so choosing of this curve is important. I will put a star here. I will explain it later why I have chosen this curve only, right? And plugging this here, I will get then f dash 0 equal to limit, since everything will be converted in x now, so I will write limit x tends to 0, right? And it will become x cube multiplied by mx cube, and I think that will be yeah, that will be m times x to the power 6, and here I will have x to the power 6 common, and inside bracket I will have 1 plus m, right? Okay, and x to the power 6 will be cancelled, and I will be having m over 1 plus m, right? And you can see that the value of the derivative is depending on m, means the limit is not unique, depends on m, right? And you can choose any m, and for any value of arbitrary m, you will get different values of f dash 0, right? So we cannot say that this is differentiable at origin, because f dash 0 is not unique, right? Therefore f dash 0 doesn't exist, or you can say that f is not differentiable at z equal to 0, right? And let me explain how I have selected this particular curve. The key point is that you see this, the biggest power of these two expressions is x to the power 6, this is y to the power 10, and you can see that this is a bigger y to the power 10, and put y to the power 10 is equal to m times the under term 6, right? And you can see that y to the power 5 is also present here. This is y to the power 5, and since you need y to the power 5, then you will square root it. You will get y to the power 5 is square root of m x to the power 3, right? But that will make the calculation difficult due to the presence of this square root factor. So rather taking y to the power 10 equal to mx to the power 6, if I take here m square, then this I will get rid of this square root also, right? And that will make my calculation easier, right? So this is the point you need to know, the selection of the curve, and see this y to the power 5 is equal to mx to this same, right? Suppose it is x to the power p and y to the power q, right? And q is bigger than p, fine. Then you will substitute y to the power q is equal to m times x to the power p, right? Similar to this one, fine. Okay, so I will take another example. Okay, example number 3, and let me take discuss the analyticity of, I will take a simplest function fz equal to z square, right? And fine, and find f dash z, right? The derivative is also required. A solution. You can see that this is a polynomial, and all polynomials are entire functions, right? Entire function is a function which is analytic throughout the complex plane, right? So this is a polynomial. It will definitely, it will be an analytic function or entire function, more general, and its derivative will be 2z, right? The same rule of derivatives are applied here as we use in real calculus, right? But I will use CR equations this time, breaking the function into a real and imaginary part, x plus eta y whole square, right? Then I will open the square, I will be getting x square minus y square plus eta times 2xy, and you can see that this is the real part, this is the imaginary part, right? Here u is equal to x square minus y square and v equal to twice of xy, and you can see that clearly. If you find del u over del x, you will be getting 2x, and if you find del v over del y, that will be same, right? And u y is equal to minus of 2y is equal to negative of q vx, right? Fine. So CR equations are satisfied, and they are satisfied for whole complex plane, right? And also these u, v and partial derivatives are continuous throughout the domain D, right? Also u, v, ux, uy, vx and vy are continuous on whole complex plane C, right? Means that the function is analytic. Therefore fz equal to z square is analytic on whole complex plane C, and we call it entire function, right? And what about its derivative? The formula for derivative is f dash z equal to del u over del x plus eta del v over del x. And note that this formula actually appeared in the derivation of CR equations, right? While deriving the CR equations, when we choose the path, that is delta y tends to 0, right? And then we got this, right? And the second time we choose the path delta x tend to 0, then we got something like del v by del y, and here we had minus eta del v over del x, something like that, right? del v by del y minus iota del v u by del y, right? Okay, so you can use any of those results, right? I'm using this one, and plugging the value of del u over del x from here. Where is my del u over del x? This is my del u over del x, 2x, and iota times del v over del x, and where is that? Del v over del x, that is 2y, right? Plus iota 2y, and you can take 2 common, x plus iota y, and that will become twice of z, right? And that is indeed the same if you directly differentiate it with respect to z, that will be 2z. The power rule of derivative, you will get 2z, same result, right? Okay, now I will derive CR equations in polar form also. These are the CR equations in Cartesian form. Deriving CR equations in polar form, because polar form is also important when you deal in complex plane. The polar form representation of a complex number is more powerful, right? And I will derive the CR equations first, right? The CR equations in polar form. In polar form, CR equations become del u over del r is equal to del v over del theta, and here we have r, and del u over r del theta, and equal to minus del v over del r, right? We have to remember these CR equations. However, a trick to remember them is that if you remember these CR equations in Cartesian form, that is del u over del x is equal to del v over del y, and del u over del y is equal to negative of del v over del x, right? You have to remember the Cartesian form of CR equations. Then you can easily write them by just replacing del x by del r and del y by r del theta, right? Okay, now I will derive them. Derivation is small, and let fz is equal to, the function is u plus iota v, or should I take z equal to x plus iota y? Okay, u plus iota v, u plus iota v, be analytic, right? Analytic or differentiable, right? Fine. Let z equal to x plus iota y. You know that z is equal to x plus iota y. Fine. Put x equal to r cos theta and y equal to r sin theta, right? You will get then z is equal to r cos theta plus iota r sin theta, right? Plugging the values of x and y here. We are actually converting a complex number which is in Cartesian form into polar form, right? In r theta form. And I will show that why I have put this r cos theta and r sin theta. If you see that if this is a complex number, this is y axis and this is x axis, right? And this is origin, fine. And you have this point P. The coordinate is x comma y, right? And you join this P to the origin O, right? And let the length of this OP is r, and let this line OP makes an angle of theta with the positive direction of x-axis, right? Then you can easily see that if you find this projection of this OP on x-axis, then this will be r cos theta by simple geometry. Applying cos theta equal to base upon hypotenuse, this length will be r cos theta, right? And this length will be r sin theta, right? This point is B. So you can see that the coordinate of this point can be written in terms of r theta, and this will be r cos theta, or P r cos theta comma r sin theta, right? So this is the point why I have chosen this x equal to r cos theta and r sin theta, right? And this will ultimately become r inside bracket cos theta plus eta sin theta, and that will be e to the power eta theta, right? Fine. Therefore, my fz will become f r e to the power eta theta equal to u plus eta v. Fine. And now I will differentiate it with respect to r and then theta, right? Because u is also a function of x and y originally, right? But since x and y are further expressed in terms of r theta, so u and v are functions of r and theta. You can differentiate this equation in term with respect to r as well as with respect to theta. So differentiating with respect to r partially first, with respect to r partially, right? Then it will be f dash r e to the power eta theta, and since we are differentiating with respect to r partially, so e to the power eta theta will appear here, and that will become del u over del r plus eta del v over del r, right? And let me call it equation number 1. Fine. And yeah, differentiating with respect to theta partially, that will be f dash r e to the power eta theta, and differentiation of it will be eta e to the power, no, I think r will also appear, yeah, r e eta e to the power eta theta equal to del u over del theta plus eta del v over del theta, right? Now, yeah, plugging the value of this one using equation number 1, if you see that this f dash and e to the power eta theta, substituting the value of this f dash into e to the power eta theta here, using first, here I will have r times eta r, and f dash into e to the power eta theta is replaced by the value del u over del r plus eta del v over del r equal to del u over del theta plus eta del v over del theta, right? And then multiplying this eta r inside, or taking this r here in the denominator, I will get eta del u over del r minus del v over del r equal to del v over del theta plus eta 1 by r del v over del theta, right? And now you can compare the real and imaginary part on both sides, because the real part is this one and this is my real part, comparing them. Yeah, equating imaginary and real parts, imaginary and real parts. First I will compare the imaginary part, and there is here del u by del r equal to, the imaginary part is 1 by r del v by del theta, and now I will compare the imaginary part, and that is del v by del r is equal to this much, 1 by r del v by this is, I think this is u, yeah, del u, fine, del u by del theta equal to minus of del v by del r, and you can see that these are the same equations, right? Okay, fine. Okay, so these are the CR equations in polar form, and we'll be using in our numericals, in which the fz is given in terms of r theta, right? Okay, and one more thing, the formula for derivative, similar to this formula as we used this formula, this one, to finding the derivative, to find the derivative of a function, we have this formula. You can see this equation number 1, you see this equation, and if you bring this e to the power eta theta here, then we'll have function formula for f dash, right? Okay, I will write the formula from first f dash r e to the power eta theta equal to, that will appear on the right hand side, eta theta and del u over del r plus eta del v over del r, and this is the formula for derivative, right? If the derivative is required, then we will use this formula in polar coordinate. Okay, and I will take one example of this polar form. Example number 1. Discuss the analyticity of fz equal to log z, right? And you can see that the function is given in terms of z, right? And if you want these CR equations to come into play, you have to first convert this function into polar form, right? Okay. Solution. Converting into polar form, right? And that is very simple. You can use this result directly. Z equal to r times e to the power iota theta. You can use this thing also, right? In polar form, Z is always equal to r times of e to the power iota theta. So I will use this Z here. It will become f r e to the power iota theta equal to log r e to the power iota theta, right? And then you can take log r plus log r e to the power iota theta, and then iota theta. Ultimately, it will become iota theta, right? And you can see that the real part is log r and the imaginary part is theta. So therefore, then clearly u equal to log r and v equal to theta, right? And yes, then finding their derivatives with respect to r and r d theta. This time we'll be using CR equations in polar form. Remember that. Finding del u over del r, and that will be 1 over r, right? Del u over del theta, that will be 0. Del v over del r, that will be 0, and del v over del theta, that will be 1, right? And we can see that del u over del r, clearly del u over del r is equal to 1 upon r del v over del theta. You can see that if we divide this by r, then it will be 1 by r and 1 by r, those will be equal, right? And similarly for the second CR equation, and del u over r del theta minus del v over del r, you can see that 0 is equal to 0, fine. Means CR equations are satisfied, right? Okay, but about the continuity of u, v, del u by del r and so on, these four partial derivatives. Actually, you can see this del u by del r, this is not continuous at r equal to 0, right? Since u, v, ur and so on, or should I write it a ur? Ur is not, ur means del u over del r is not continuous at r equal to 0, right? Means that the continuity criteria of u, v and its four partial derivatives is satisfied over the whole complex plane except the point r equal to 0, means the origin, right? But CR equations are satisfied over the whole complex plane. So the result will be that their intersection, means CR equations are satisfied for the whole complex plane, but the continuity criteria is satisfied for the whole complex plane except the point z equal to 0, right? So we'll exclude that point and we'll say that the function is analytic over the complex plane except the point z equal to 0, right? That is C, the complex plane, and then 0 excluded from it. Means 0 means r equal to 0, you can say z equal to 0, right? The origin z equal to 0 is represented by r is equal to 0 and theta is undefined there, right? You should remember this point. If you take z is equal to 0, and this is the origin z equal to 0 on xy plane, and you want it to write in polar form, then the polar representation of z is equal to 0 is r is equal to 0 and theta is not defined there, right? Okay, and why theta is not defined there? Because theta is actually tan inverse y upon x. If you go into the detail of this thing, then theta is actually tan inverse of y upon x, right? And you can see that if you divide this x equal to r cos theta, y equal to r sin theta, if you divide these two, you will get tan theta equal to y upon x, or theta equal to tan inverse y upon x. And tan inverse y upon x will produce a tan inverse 0 upon 0 at the origin. If you are taking z is equal to 0, it means that x equal to 0 and y equal to 0, then theta will be tan inverse of 0 by 0, and that is not defined. That's why at origin you just write r equal to 0, right? Theta is not defined at the origin, right? So you can see that this partial derivative or this u function is also, this is not defined at r equal to 0, right? Again, this v is not defined at r equal to 0 because theta is not defined there, right? So u, v and del u by del r, these are not defined. I should write here u, v and del u by del r are not constants at r equal to 0, or even they are not defined at r equal to 0, means we have to exclude the point z equal to 0, right? So we can comment that the function is analytic on the whole complex plane except the point z equal to 0, right? Therefore fz is analytic on C oblique 0, means 0 is deleted from the whole complex plane, right? Okay, and if we are asked to find the derivative also, suppose if I add here calculate f dash z also, right? Then I will use this formula. Where is that formula? This formula, right? Also f dash r to the power iota theta equal to e to the minus iota theta del u by del r plus iota del v over del r, and plugging these values, del u by del r is actually 1 by r e to the minus iota theta 1 by r plus del v over del r is 0, fine, and it will become 1 over r e to the power iota theta, and that is actually z. You can see that z, right, equal to 1 over z. And indeed directly if you differentiate this log z, then you will get 1 over z, right? But notice that this is not differentiable at z equal to 0, and if it is not differentiable at z equal to 0 and except that z equal to 0, it is differentiable everywhere, right? So we can say that it is analytic, right? So be careful while commenting about the analyticity or differentiability behavior of some function which is satisfying the CR equations or the whole complex plane except a single point, right? So this is it for CR equations. We have discussed both CR equations in both Cartesian and polar form, and in the next video we will be discussing about the behavior of u and v, right? Till now we have been discussing about this fz analytic function, its differentiability, its continuity, its limit, right? But now we will get an insight into the u and v. U is the real part of function and v is the imaginary part of analytic function, and what are their properties of u and v, especially when they are part of an analytic function. That will be the part of our next video, right? And for this video, thanks.